All right, next we're going to talk today a little bit about a strategy for how to find limits. We've talked a lot about properties of limits. Now let's talk a little bit about how can we actually determine a limit. So here's theorem 1.7. You have functions that agree at all but one point. So you have two functions here. You've got f of x and g of x, and they're the exact same function for every x in the open interval as long as x doesn't equal this one value c. So they agree everywhere. They're the exact same thing except for this one point. So if you just picture one little spot where the one has a hole and the other one does not. So it says if the limit of g of x as x approaches c exists, then the limit of f of x also exists, and the limit of f of x as x approaches c is equal to the limit of g of x as x approaches c. So the limit is the same for that value of c, even though one function is not defined as c at c and the other one happens to be defined at c. Here's an example. So you've got the function x cubed minus 1 over x minus 1. We want to find the limit as x approaches 1. All right? So hopefully you guys can see by now that when I direct substitute a 1 into the bottom of this, into the denominator of this expression, I get a 0. Right? So I can't do a direct substitution to find this limit because it's undefined when x is equal to 1. But we can rewrite f in such a way by rewriting the top. And so x cubed minus 1, that's the difference of two cubes. And so I'm going to write x minus 1, factoring out that perfect cube. And that leaves me with x squared plus x plus 1. Have to go back to some of the strategies we did in Algebra 2. But when you see things like this, you should check if you can factor them, and oftentimes you can. All right, and so you can see down here in the bottom it's written much more neatly. If you take and cancel or divide these two factors out, then you're left with x squared plus x plus 1, which is a function that is defined when x equals 1, right? If I put a 1 into here, then I'm going to get 3. And so these agree everywhere, these two functions. We'll call the second one g of x, and we call this first one f of x. They're the same function except for just that one spot. Like if we graphed them on the calculator, you'd see that they look exactly the same except at just that one spot. So here's a picture of the two of them. So this is f of x equals x cubed minus 1 over x plus 1. You can see here's that one spot when x equals 1. We've got that open circle there. But then when I rewrite it and cancel a factor, I end up with it being defined at that one spot. So these two functions are exactly the same, except just that one spot when x equals 1. That theorem we said, they agree all at one point, and so we can apply theorem 1.7 and say that then the limit is what we would get by direct substituting into x squared plus x plus 1, and we get 3. So here's the whole process. You factor it, you rewrite it. So here's the second function that is defined at 1. Divide out the like factors. Apply the theorem 1.7. So now we're going to take the limit of this. It's a function that agrees with the other one except at that one point. 1 squared plus 1 plus 1. So we get 3. If I can ever get to the end of the slide here. There we go. And to simplify, and you get 3. So here then, going back one, is a strategy for how to find limits. This is just one strategy. Learn to recognize which limits can be evaluated by direct substitution, which we talked about. So we had all those theorems in the last section that can be evaluated by direct substitution. All of these are in theorems 1.1 through 1.6. We looked at all those in the last video. If you've got a function that cannot be evaluated by direct substitution, such as that one where we had something that would have equaled 0 in the bottom of a fraction, that can't be evaluated by direct substitution, one way to try to get the limit is to find another function, g, that agrees with f at every point other than just that one point. So in the last example, it was when x equaled 1. And so we choose g such that it can be evaluated by direct substitution. So we're looking to rewrite it so that we can analytically just evaluate it. And then we apply that theorem that we just showed to conclude that the limit of f of x as x approaches c, we rewrite the function to get a new g of x, and it actually ends up being g of c. And oftentimes it's helpful to use a graph or a table to reinforce what you just saw, as we did in that last picture.